Hello, thank you for watching this online lecture for Research Methods 1. This lecture is an introduction to statistics, and as the course progresses, of course, we will build further on this. So this is the first step into talking about statistics and looking at some of the words that we will need to know and concepts that we'll need to learn. As an example, we'll talk first about the 2012 national elections. In these elections, there was this party that has been participating in these elections for quite some time now, and it's the PVV, Party for Freedom, as it's called, run by this guy you see on the top right, Geert Wilders. This is a xenophobic right-wing party, and so of course there's a lot of interest amongst political scientists and the like to understand which kinds of people vote for this party and why they do so. And we'll use this as an example to talk about some of the concepts that we'll need for talking about statistics. So things like population, what that means in context of statistics, sampling, and that sort of thing. So let's look at some of the data that we know about this. On the right-hand bottom corner, you see a map, a sort of a heat map of the Netherlands, and where this party got the most votes. And as you can see, you might know where you are in the appendix at the bottom there. That's where Maastricht is. And you see that this province around it called Limburg is very purple, meaning this is a place where Geert Wilders received a lot of votes. And so there's different explanations for why this might be. And as by means of an example, let's look at the results specifically in Maastricht. And this is what happened over here in 2012. And so we see that the Social Democrats received the most votes at the time as a percentage. So 28% of people voted for the Social Democrats, followed by the Conservative Liberals. These are my translations, by the way, so there might be color in the translation. There's the VVD for those who speak Dutch. And then in third place, we see that the PVV, the xenophobic right, as I've translated it, received 15% of the votes. So let's say that we wanted to run a little study to understand this better. Okay, so here's a map of Maastricht. It's colored in black and white, but you might recognize it still. Let's see if I can put a pointer on the screen. I don't think that's possible at the moment. No worries, we can color. So UCM would be somewhere around this area, just for your navigation. The Vrijthof would be somewhere in this area here, and then we have the Market Square over there. And so let's say that we ran a little study to understand which people vote for this xenophobic right-wing party and why they do so. So this is Maastricht. How would you go about sampling? In other words, finding a group of people that you'd want to interview to have a representative sample of the bigger population. So at this point, we need to talk about what population, sample, and N mean in this context. Population, of course, we all know the word population as referring to, for example, the population of a country or a city. But population in statistics means the group of things or people that you want to generalize things to. So in this instance, the population of Maastricht is also the population in statistical terms. But that means every single person in Maastricht in this example. If the population was, if we did a study on pebbles on a beach, or grains of sand on a beach, that every grain of sand would be part of this population. The sample then is the subset that we take from that, so the grains of sand that we take at random, or in this case, the people that we interview at random or using a certain strategy. Then finally, N refers to the size of the sample. In other words, in this example, how many people did we talk to? So let's say that we wanted to draw a sample from Maastricht. And we wanted to say, okay, we're actually in this circle here in the middle, UCM is over here, so it might be pretty convenient to just take people in the center and talk about, interview a bunch of those people and ask them, did you vote for the PVV? And if so, what made you do that? Of course, maybe this is not a great way of sampling, right? There's other ways that we might explore. For one thing, perhaps there's more people who with a higher income who might live in the center. Perhaps alternatively, there might be a lot of students who live in the center as opposed to the outskirts of the city. And so we don't know at the moment where these PVV voters are in the first place and whether maybe per area, there's a difference in reasons why people would vote for that party. So let's think about how we might do this differently. And for that, we need a little more information about what Maastricht is like in terms of politics. And I looked up the numbers for this. So what you see here, the way elections are organized in the Netherlands is that there's different voting booths at which people can go and vote. In principle, this is voluntary, by which I mean they can go to any one of these dots. So every dot is a place where people can vote. However, research has shown that most people will tend to go to simply the one that is closest to where they live. And so in some ways, this might be a fairly reasonable indication of which areas vote how. Now, this map is not particularly revealing because it just shows you the biggest party per voting booth. And so you see most dots are red, as we've established. That's the PvdA, so that's Labour, in other words, the Social Democrats. And then we have some light blue colored dots, which is the VVD, which is the conservative liberals, as I called them earlier on. So the neoliberals, basically. And so by this we can say, all right, we might actually hypothesize a couple of things here. So for example, some of you might know that this area here is actually the more wealthy part of town, and you see that indeed they vote for the neoliberals. There's a bunch of that in the center as well, which for the same reason might make a lot of sense. And then most of it is the Social Democrats. This doesn't say anything about the votes for the PVV, though. For that we need another map, and that's this one. So here what you see is the darker the shade of purple or blue or whatever it is, the more people as a percentage of people living there or casting their vote, the higher the percentage of people who vote for the PVV. So this is specifically about PVV voters. So you see that actually, again, in the center and in this wealthier area, there's actually very few people who have voted for the PVV. But then there's these outskirts, basically. So for example, here is a very strong hold of the PVV voters. There's a bunch of stuff here. And then there's a whole lot of people here. So I happen to know from living here that these are areas that are lower socioeconomic background, you might say. So these are people who have lower education overall, a lower income as well. But also these are areas that are very high in the percentage of immigrants who live there, which is of course one of the things that the PVV despises. So in sociology there's this contact hypothesis, which can go two ways. One is that if people are in contact with other groups of people that they might not like, so in the case of PVV voters this might be immigrants, then contact breeds actually understanding. So they might get along better and therefore not vote for the PVV as much. Alternatively, the contact hypothesis can go the other way. So the more you are in contact with these other people that you don't like, the more you're annoyed by their presence, and therefore the more you might support the PVV in this case. So the second hypothesis seems to be more feasible here. So, but let's say that we wanted to actually sample here. And for that we need to kind of think about how we address this sample, because it is possible that of course there's still some people who voted for the PVV in this area, as an example, or over here. These are less poor areas, but nonetheless there's some people who voted there. What might be their motivations, and are those motivations different from people in this area here, for example? So perhaps sort of a geographic spread of the way that we sample would be good. So perhaps we could say, for example, let's say there's about 120, 130,000 people living in Maastricht. We can look up from the municipality how many people live in every area, and then let's take a percentage of every area, so that we have a representative sample, not of Maastricht alone, but also per area, so that we can make some claims about what's happening in different areas and how the urban landscape, for example, might impact on that. So to recap, we have a couple of terms that we have been using here. We have the population, which is every thing or person in your study. So the thing that you're generalizing to, the thing that you're making claims about. Then within that we have what's called a sampling frame, which is the way in which you define who is in and who is out of your sample, how you sample, in other words. So in the previous example, we looked at geography and how different neighborhoods might be different. So that is part of our sampling frame. We might also have part of a sampling frame. In this example, we might have age, or maybe educational background. So perhaps we want to have a representative sample of higher and lower education, higher and lower income, etc. So in other words, it's identifying the factors that determine how people or things might be different in on the thing that we want to study. The sampling frame then, of course, instructs us on how we go about getting things or people, and that is called a sample. And the size of the sample is called the N. It says 22 here just because I counted the people that you see in this box. Okay, so once we do the study, we want to identify what is it that we are talking about. And the things that we are talking about when it comes to statistics, we call them variables. Variables are things that we measure, in essence. So there's a couple of different types of variables that I'd like to talk about now. We might talk about more different types in the future, but for now, I want to focus on independent variables. That is, we write that down as X usually. And there's a thing that's causing something that we are interested in. And we call it the independent variable because for the project, for the study that we're doing, we assume it to be independent of all of the other things that we are looking at. Then we have the Y variable, which is the dependent variable. And it's called the dependent variable because its value, its score, how high it is, depends on the value of the independent variable. So for example, if we say that perhaps age impacts on how likely people are to vote for this right-wing party, then we might say the higher the age, the more likely the vote for the PVV will happen. And so X is causing Y to an extent. There's another two types that I want to talk about. One is confounding variables. There's different words that people use for this, but let's use confounding in this course. And these are, this is basically a criticism that people might have. So let's say that you do your study on voting for this right-wing party in Maastricht, and someone reads your study, reads your report, and they say, well, you didn't look at gender. And from other research, we know that gender is a big impact on whether people will vote for the radical right. Women are much less likely to vote for the radical right. So you might then say, okay, well, that might be a confounding variable, something that I should have looked at but didn't. I didn't include it in my study. The solution for a confounding variable is called a control variable. So a control variable is something that you measure in your study, but is not your primary concern. So perhaps your study is about whether higher or lower incomes will cause people to vote for the PVV or the radical right. But someone says, well, you should also include gender. And you say, well, okay, but gender is not my main interest, but I'll include it in my models just to make sure that that's not actually what's causing it. Yeah, so that we call a control variable. As a brief note, considering we have computer lab sessions coming up, and we'll use a computer program called SPSS. I could look up what these letters stand for, but this is just the name of the program. There's other programs like SPSS out there. SPSS is not the most ideal program, perhaps, for doing statistics. It's used a lot. It's less flexible than some other programs, but the big advantage that it has is that its learning curve is slightly less steep than other programs. So where in the competition to SPSS, you would be programming basically to get what you want, or you're writing commands to the program. SPSS is menu-based mostly, so you click through boxes, and that's a more familiar interface. And this is why that's what we're using in this course. And just to give you sort of a preview of what that might look like, we'll build on this in the lab sessions. This is what data looks like. So data is nothing more than basically a spreadsheet, as you can see here. So in this example, we see that we see all the variables that are measured, and these are names of variables over here. And there's a description of what it is like, what it is measuring. So do people trust TV? And all sorts of other types of things and how it is measured. We'll talk about what this is in the lab session itself, but just so you have a little preview of what data looks like to demystify it a bit. The next chapter, so to speak, that I want to talk about is describing a sample. So that might also be the first step that you do in a paper that you do using statistics, which is there might be two things that you're doing. There's describing the sample that you took. So for example, in the example of the radical right, you're just giving a table of, I interviewed this many women, this many men, the average age of the sample was this and that, then this many percent of people voted for the PVV, this other percentage did not. etc. Just describing it. The second phase of a paper like that often is to look at relationships. So is there an impact from age on voting for the radical right? Yeah, but let's first look at just describing it. To describe any sample, we want to talk about variance. And variance is nothing more than just how much does something vary. So the variation in a certain measurement. So for example, in the picture that you see here, we see three men, a tall man, a medium man, so to speak, and then a shorter man. And so height varies. If we were to measure the length of all the UCM students, we'll get some sort of diversity of measurements. None of you are exactly the same height, most likely. The thing with the variance, though, with most variables that we can measure, especially when it comes to the social sciences, but also in the natural sciences, this happens quite a lot, is that it varies around a certain central tendency. And that's just a complex way of saying there's a middle that describes most of the observations. So we'll talk a bit more about that. Here's an example in the form of a table that we might do, right? So if we measured a bunch of, let's say that these are high school students, considering the length here, you see that there were 4 students there who were 1.40 meters tall, and then there's 5 of them who are 1.80 meters tall, but most of them tend to kind of clump together around this 160 mark, where the central tendency then is. So how do we describe the central tendency then? One way to do this would be to use what's called a histogram. And a histogram is basically this table that you saw on the previous slide, tilted on its side and represented by bars. So again, we see that in the middle we have these 160 length students, and then we have a couple of people who are around this 180 mark, and then a couple on the lower side. But generally speaking, most of the students were in this middle central tendency here. So that's what we call the center of a distribution. And so the thing with statistics is that as we increase the size of a sample, we get more of a picture of what the actual population might look like. So you see this represented here in this graphic. As we increase the n, the sample size, the pattern becomes more and more clear. So you see that the line that describes it becomes more and more fluid. So n is 4, n is 8, n is 16. And so as we increase our sample, the distribution becomes more clear. We can use some statistics essentially. So these are statistics is a big word for these things because you're familiar with what these are. We have a couple of things that we can use. We have the mode, the mean, and the median. What you see here is a mean cat. So that's a joke, just to be clear, a very lame joke. Statistics jokes tend to be very lame. But there we have it. So the mode is the most common value in any distribution. So in the previous slide, we saw that might not necessarily be 160. It was actually another length that was the highest bar, meaning that's the most people chose that category. The mean is simply the average. So the average means adding all of the values together, all of the lengths of students, we add them up, and then we divide them by the number of students that we measured. Yeah? So that's the average. Most of you will be familiar. The median then finally is simply the middle of the distribution. So if we count to 5, 1, 2, 3, 4, 5, then 3 would be the median. It's the middle value. Regardless of how many people chose any of those values, the median will be the middle value. If we wanted to represent this graphically, you could see it would look something like this. So again, this might be a histogram, but sort of graphically represented by a line instead of bars. And just by knowing the numbers for mode, median, and mean, we can already tell something about how skewed a certain distribution might be. So in the straight lines on top, that's pretty symmetrical, right? And we also see that the mode, which is always the peak of any one of these lines, right? Because it's the most common value, the value that was chosen the most, is right in the middle there. But then the median is actually not that far off, which is the middle value. And then the mean is also pretty close to those things. If they were exactly the same value, so let's say that the mode and the median and the mean are also all, say, 5, that means that it's an exactly symmetrical distribution. In the dotted example that you see at the bottom there, so I'm going to draw sort of a line to show you what I'm talking about. We have the same median actually in the middle. We see that this green overlaps with the two distributions. So the middle value is the same. In other words, the maximum and the minimum value of this distribution are exactly the same. But the mode is much lower over here than it was with the straight lines, because that's simply where the peak of that distribution is. That's the most chosen value. And then the mean is much higher. This is because there's a couple of extreme outliers to the side, which kind of pull their weight. They pull the mean towards them. Just because if you imagine measuring a bunch of students, and most of you will say, I'm 160 centimeters tall, but then there's one extremely tall person and they say, I'm 2.5 meters. Say. So this person who's 2.5 meters will add to the mean by saying, we're adding 2.5 meters to it, but we're only dividing by one more person. So that means that the mean is inflated by just this outlier. So this is all relating to skewedness. So very briefly, the middle you see here, a normal distribution with no skew. And so the mean is the median is the mode. Then we have a negatively skewed distribution here where the mode is higher than the mean, which is higher than, the mode is higher than the median, which is higher than the mean. And of course we have a skewedness in the other direction. We call this positively skewed, where the mean is higher than the median, is higher than the mode. So even if you didn't have these visuals to help you, if you just had the numbers, we would already know something about how skewed a certain distribution might be. Another thing that is relevant when we're talking about distributions and describing a sample is something called the standard deviation. Some of you will be familiar, others might not be. For those who are hearing this for the first time, bear with us. It sounds more complex than it actually is, I think. So we use the Greek letter sigma to signify it. I don't need you to remember this. I'm just telling you, if you see it mentioned somewhere, you know what they are talking about. But basically what it is a measure for the extent to which a distribution is spread out. So in other words, the higher the value, there's a number associated with the standard deviation. The higher that number, the more spread out it is, the more diverse your sample is. In addition, it's also used to measure confidence in statistics. So we're moving in the direction of statistical significance, as that is called. So I'll talk more about this later, but these are the two things that we use it for. So how spread out is it, and how confident are we about making certain claims about relationships? So standard deviations are called standard deviations because they are standardized. And they're called deviations because they measure the extent to which something is deviating from the central tendency. So in this perfectly normally distributed example here, the central tendency is here. Because it is exactly symmetrical, the median is the mode is the mean, so we don't need to get into that. But the standard deviation, the trick is that is always a set percentage. So at the bottom here you see a couple of percentages, and these are rounded off, by the way, and that's enough. That I don't need you to know the exact percentages, but this indication would be good to kind of remember. And so from the center it goes in both ways, right? So from the average it goes one standard deviation to the left, one standard deviation to the right, both of which are 34% for this first standard deviation. So you see +1 SD here and -1 SD here, which means +1 standard deviation from the center and -1 standard deviation from the center. And this first standard deviation is always 34%. 34% of what? Well, 34% of the sample, of the people in this example or things that we measured, and 34% is also the area basically of this slice here, and also 34% here, which means that in total, one standard deviation from the center to the left and to the right, we have 68% of all of the observations, right? So if we measured your height again, then 68% of you will be in this within one standard deviation, plus and minus. And it tapers down from there. So the second standard deviation is 14% to the right, also 14% to the left. And the third standard deviation is 2% to the right, 2% to the left again. And so you see, of course, this area is also much smaller. So there's only 2% of people who will fall into this course. Just to show you visually how that corresponds to different distributions. So these are two simulated distributions with the same average. So the average between the blue and the red are both 100. It doesn't matter what we're talking about. This is a simulation. It doesn't refer to anything real. But let's say it's centimeters of some animal. So maybe this could be dogs and cats, let's say, right? So dogs, as a rule, would be more diverse than cats, but these are pretty sizable cats at 100 centimeters. But let's roll with it. So if red is cats kind of vary between 60 centimeters long and 120 centimeters long. Just assume that we have very, very tall cats. Dogs are also on average 1 meter tall, but they vary between 0 centimeters, which of course is an unrealistic value, and 2 meters 30, which is a huge dog as well. Right? So dogs are more diverse, meaning their standard deviation value is just simply higher than that for cats. Right? So the higher the value, the more diverse. Now we're ready to move on to describing relationships. So like I said, in any given paper that uses statistics, there might be two phases. One phase where we describe the sample, and the second phase where we look at relationships. And this we call descriptive statistics, which is describing a sample, versus inferential statistics, inferring a value on a y variable based on the values of an x variable. So often these descriptive statistics use graphical and numerical descriptions of your data, whereas the inferential make generalizations, right? So this is where generalizing from your sample to the population comes into play. So let's look at some of the descriptive charts that we might use, so graphical representations. First of all, we have the pie chart. We all know it. So perhaps these are UCM concentrations. I don't think this is actually correct, but there we have it, right? But that's a useful way of showing concentrations. Why? Because concentration is what we might call a nominal variable. Nominal just means we measure a certain thing, but the thing that we measure only has categories in no particular order. So yes, it is different if you study social sciences or humanities, but they are not higher or lower than one another. It's just different categories. Another example might be, what's your favorite ice cream? Is it strawberry flavor? Is it vanilla? Is it chocolate? Those are not in a specific order, but they are different categories. And for that, a pie chart is usually a good way to represent that graphically. We also have bar charts. You're all familiar. Of course, this is not real data, but simulated data. Bar charts tend to be good for what is called ordinal data, or sometimes scale data. I'll talk about scale data in a second. Ordinal data is like nominal data, so it doesn't have a specific numerical value. So it's not like social sciences is 1, humanities is 2, sciences is 3. That's kind of arbitrary to give those numbers. So that way it's different categories, but in this case, categories are in an order. So a good example here might be level of education. So we have people with just a primary education, we have people with secondary education, and people with a tertiary or university education. We can't say exactly that university education is 3 times as much exactly as a primary education, but at least it's more education. So it's in an order. And then we have what's called scale data, and scale can be taken apart into interval and ratio, but we'll talk about that some other time. But scale data basically is where we have measurements of an exact thing. So for example, age would be a scale measurement, where we could say someone who's 20 years old is twice as old exactly as someone who's 10 years old. Okay, so, or if it takes you 15 minutes to go to UCM, from your home, that's 3 times as long as someone else who it takes 5 minutes to go to UCM. Yeah, so exact measurements with an exact numerical value. Example here is shown in a scatterplot. A scatterplot is basically 2 variables. In this case, the husband's age. These are heterosexual marriages, as an example, and the wife's age at the time of marriage. And fortunately, there seems to be some relationship between the two, because every dot represents one marriage. So for example, this dot over here is a marriage where the husband was, let's say, what, 48-ish, and the wife was 37-ish. Yeah, I'm kind of estimating here. And so every dot is like that. And what we'll be doing with inferential statistics, amongst other things, is to look at relationships, patterns that we see in data like this. So what we see here is kind of a relationship that goes up like this, which simply means the older the husband is at time of marriage, the older the wife also tends to be at the time of marriage, which is kind of an obvious statement in most places. One way of analyzing these types of relationships, so keep scatter plots in the back of your mind, is through what we call correlation. And the most common notation for correlation is Pearson's R coefficient. This sounds like a mouthful. Pearson is just the guy who came up with it. R means correlation, and coefficient is the way it's expressed here. And this is what scatter plots might look like graphically. So a correlation, Pearson's R coefficient, ranges always between -1 to +1, where -1 is a perfectly negative correlation. So you see that here at the bottom right. Which means that if it's exactly -1, that means that we can exactly predict one thing by the other, right? So if this was husband's age and wife, they would be exactly the same age basically, or at least the age would decrease in this case, which is odd, by exactly the same amount. The inverse would be exactly +1, which is a perfectly positive correlation. So we can almost predict for certain what it will be. In the social sciences especially, but in other fields as well, R coefficients tend to be somewhere in between, because it's never really a perfect correlation, perfect relationship between things. There's always exceptions. And so these are example values: 0.8, 0.4, it could also be 0.2, 0.325. We have everything in between. And so you can imagine what that might be, right? So the higher the number, the stronger the pattern, basically. So 0.8 is a pretty high, pretty strong pattern, whereas 0.4 is a slightly weaker pattern over there. Still in the same direction, but weaker, because the distance between all of those dots will be bigger overall than over here. Yeah. Then a correlation of 0 means there's absolutely no relationship at all. There's no line that we can draw. It's just basically a fluffy cloud of randomness. So no relationship. That's what correlation is. In the next lecture on statistics, we'll build on this, because we will need different ways of approaching these relationships between two variables, depending on how we measure things. But that's something for another day. Correlation is where we start. Of course, correlation does not imply causation. That's something that needs to be stressed in any sort of introduction to research methods. And here's some examples. I'll put a link on the website where I got this from on the student portal, because basically what you see here is time series data, where they looked at the per capita consumption of cheese in the US, so how much cheese does every person on average consume in the United States, correlated with the number of people who died by becoming tangled in their bed sheets, which of course is nonsensical that there would be a correlation, but this is a correlation that's almost perfect, 0.99. I wouldn't know of any way to explain this exactly, unless people tend to eat cheese in their bed, I don't know, and maybe they eat cheese that makes them drowsy. I don't know what the relationship might be here. I don't think there is one. It can also just be random noise that happens to correlate. We have random chance in the world. Here's another one. Another one, which is a perfectly negative correlation, almost. Let's see, that was 0.93, which is almost a perfectly negative correlation. And it's between honey-producing bee colonies in the US, so the number of them, and the juvenile arrests for possession of marijuana. Again, I don't think there is a strong relationship here, but it exists. So beware of how you use correlation. SPSS, the program that we'll use, or any other program for that matter, will just run the calculations as you instruct it to. So the program is dumb in that way. It doesn't really check, does this make sense? That's up to you, the researcher. It just calculates it for you. And if there happens to be a correlation, it'll show you the correlation. It's up to you to interpret it. So some reasons generally why there might be a correlation but still no causation is that there might be a reverse causation, where not X causing Y, so not the independent variable causing impacting on the dependent variable, but the other way around. Maybe it's the dependent variable actually impacting on the independent variable, and you got it all wrong. There might also be a string of causations, so where x causes a third variable, z, let's call it, which in turn causes y. We might have a spurious relationship where there's a third variable that we didn't measure perhaps, which causes both x and another x, or x and y as you had it in your model. So for example, an example that's given a lot here is where people think that maybe sleeping with your shoes on might cause a headache, right? So give that some thought, what might be going on there. Yeah, so the z variable here would be, the z variable would be that someone went out drinking the night before and got home drunk very late, and they kept their shoes on, just kind of fell on the bed, fell asleep, but also woke up with a headache, also because of the drinking. So z is the drinking, and the two x's are sleeping with your shoes on and having a headache. And of course, there can be random chance, as I think might be happening in the examples on the previous slide. Yeah, so like I said, most jokes and comics when it comes to statistics can be kind of lame, but for those who enjoy it, here you go. All right, so maybe now it's getting more interesting. We get to testing hypotheses. We'll first talk about what a hypothesis is, and then what the procedure is in general terms of testing a hypothesis. So here's the definition. A hypothesis is a logical conjecture, a hunch or an educated guess about the nature of relationships between two or more variables expressed in the form of a testable statement. So this is a mouthful, but essentially it's a claim that you're making that you want to test by looking at data, at empirical data. And so that means that a hypothesis, usually it is deduced from a theory. We talked about this earlier on in the course. And importantly, it needs to be testable. So there's no point in formulating hypotheses that nobody can test. We need to be able to find data and analysis techniques to actually test a hypothesis and either accept that it might be true or reject it because we see that it's not true. The logic behind testing hypotheses and deduction comes largely from Karl Popper, who wrote a whole bunch of stuff, but what's relevant here is the idea of falsification. So what he says is, in the empirical sciences, by which he means the quantitative social sciences, but also, of course, the medicine, all the science disciplines, any field like that, we'll generate theories. We'll have theories that are put forward and they need to be tested. But the thing is that we can never really know for sure that something is true, definitely, because perhaps we haven't looked at all of the data, perhaps we haven't considered all of the alternative explanations. But what we can do is falsify things. We can be sure about things that are definitely not true. And so this is called falsification, and this is also the foundation for why we test hypotheses. So that means that, say we have a general theory about a certain phenomenon, say maybe it's about right-wing voting behavior, as we talked about that before. We might have a theory on that, and we say that, okay, well, if this theory that by this person who put that forward in their book is true, then this testable hypothesis also would need to be true. If this hypothesis would be false, then that undermines the theory that we assume to be true for now. And so this is falsification, and this is what we do with most types of statistics, or perhaps all kinds of statistics in some way. So hypotheses, again, there's two that we need to talk about. There's the null hypothesis, and this is sort of a hidden hypothesis in most cases. We rarely see people writing this out in full, and so in your papers that you will be writing later on, I don't need you to write out the null hypothesis in full, unless that's particularly relevant for your project, of course. And the null hypothesis is a very boring hypothesis, but it's the one that we're really testing behind the scenes. Essentially, it says there's no relationship between two things, in most cases. So as an example, we'll be talking about life expectancy in the Netherlands, just to have something concrete to talk about. And so the null hypothesis here would be life expectancy has not changed, right? It says has not risen, but more appropriately it would be it hasn't changed. It's the same as it was 50 years ago. Then we have the research hypothesis, or some people will call that the alternative hypothesis. And this is the thing that we write about typically. So this is the thing that we have a theory and we have deduce a hypothesis. And this is the hypothesis that we think might be true. And we're going to test it by using data. And there's two types of this research hypothesis. It might be directional, where we say it has gone a certain direction, or things impact on other things in a certain direction. So if age is higher, right-wing behavior will be higher or lower, right? That's a direction. And so in this example here, it might be life expectancy has risen in the Netherlands since the 1960s, let's say. And a research hypothesis can also be non-directional, where we say, well, we don't really know how things have changed or how things might be impacted, but we do think that they do impact on one another, right? We think that there might be a relationship between age and right-wing behavior, but we don't know whether a higher age or a lower age will make you more right-wing. So in the example here, such a non-directional hypothesis might be life expectancy has simply changed since the 1960s. And this brings us to statistical significance. And then first, right off the bat, it's important to talk about the difference between what we normally mean by significance. So something is a very significant event in the news, for example, meaning it has a big impact on people's state of mind about policies and politics and the world, climate change. Is all very significant. Statistical significance is not necessarily also substantively significant in that way. So statistical significance can be a very tiny effect, but we find it all of the time in the data. So for example, perhaps older people might be more likely to vote right-wing, but maybe it's a very small impact. Maybe the difference is not that big, but it is a difference that we find all of the time. So maybe it is not substantively significant. In other words, it's not really interesting, but it is statistically significant. We see the pattern. It is there. So the way that we think and write about statistical significance is by looking at two words, or two letters really. So one is alpha, and alpha is the Greek letter again, which represents how unsure we want to be when we test a hypothesis. Because the tricky thing with these types of statistics is that we never really know for sure, like I said before. What we can do is say how unsure we are. And so alpha represents its value that represents how unsure we are willing to be. And so this is up to researchers to decide. So for example, we could say we want to be, we are okay with being 5% unsure about our claims, about testing our hypotheses when it comes to explaining right-wing behavior. However, when we're testing medicine and whether people will die, perhaps we want to be slightly more sure than 5%. We can't have 5% of people dying because of our drug testing, right? So we want to be less unsure there. So we want to have a lower alpha value. Common levels used in many fields will be 10% unsureness, 10% alpha, 5% or 1%. And like I said, in medicine, it might be even lower than that, or in other fields. This again corresponds to the standard deviations that we talked about. So basically what we say is, if we find a value of, so for example, if we find someone who is 2.5 meters tall amongst the UCM students, they will be somewhere here in the observations, right? They will be significantly taller, both substantively, but also especially statistically, which is what matters here, than most of the bulk of people who will be over here, right? So most of you will be, what, 180 maybe, 170, 180. So that's where this bulk of people will be. 68% of people will be here. But then this 2.5 meter person will be over here. And maybe there's some person who's only 0.5 meter tall, let's say, and they will be over here. So then basically what we do in with hypothesis testing is say, okay, we find this certain value, 2.5 meters, 0.5 meter. How likely is it that we find this person at random, given the sample that we have? So that's actually these percentages that we find here, right? So we add up these percentages, and that give you a likelihood that you would find this person at random, based on random chance. Okay, and so like I said, there's two values that we're looking at when we are hypothesis testing. One is alpha, as I explained. The other is the p-value, and this can be confusing because they refer to the same thing in principle. So the way to think about this is that the p-value is the probability that the population value is equal to the null hypothesis. That's a complex way of saying that this is the probability that the sample result, so like I said, the 2.5 meter person, for example, is found in the population, while the null hypothesis is assumed to be true. For a non-directional hypothesis, this would be twice the size of the one-tailed p-value. That's just because we're looking in both directions, right? Not a hugely important point, but it might come up when you're doing your project. Okay, to simplify things a little bit, when we do hypothesis testing, all we do really, when it comes to this type of statistics at least, Let's not get into some exceptions right now. But with p-value based statistics, which is most of it, we compare this p-value to the alpha value. So essentially what was happening here is the alpha value is in principle set by you. How unsure am I willing to be about this? Am I testing drugs? Am I looking at right-wing behavior? Depending on what I'm looking at, I might choose a different value. And it depends on your sample size as well, but we'll get into that later. And on the opposite side of this, we have the p-value, which is not something that you choose, it's something that you get, right? So you do the calculations. In our case, we use SPSS, but it could be another program. But SPSS gives us a value that is the p-value. So it's a calculated value, which says how unsure can you be, right? So SPSS tells us how unsure can you really be about this hypothesis. You say how unsure am I willing to be? What's acceptable to me? And so of course then we need to compare these two. So if this p-value, how unsure we can be, is smaller than or equal to how unsure we are willing to be, the alpha value, then we say, okay, we reject the null hypothesis and we accept our research hypothesis. Yeah, so we can falsify, we can at least say the null hypothesis is not true, we falsified that. Yeah, and so then that doesn't necessarily mean that the alternative, the research hypothesis, is finally true, because Popper says we can only falsify, we can only reject things. But at least it's become more likely because we've shown that it's going in that direction. The data that we have supports this hypothesis. So to come back to our example about life expectancy in the Netherlands. First of all, the null hypothesis is assumed to be true until we falsify it. Here's some data. Between 1960 and 2000, Dutch life expectancy rose from 73.37 to 78.24 years at birth. So, of course, this is higher, so that seems in favor of our alternative hypothesis. It has risen. But then the question is not, has it risen, but is it statistically significant? Or might this be a random fluctuation in life expectancy? You know, might it go down again in 10 years? So let's say that we put this information into SPSS. We have a bunch of larger scale data, and SPSS spits out a p-value of 0.025. Is this then significant? We have a directional alternative hypothesis, so we don't need to double the p-value. If this is not clear, it's fine. We'll get back to this later during the project period. And so that, like I said, the p-value that we get from SPSS is 0.025. So just to recap, this p-value then represents how unsure can you be about rejecting the null hypothesis. And we've set for ourselves a significance level of 5%, which would be in p-value terms 0.05. Is that bigger or smaller? Yes, 0.025, how unsure we can be, is smaller than 0.05, how unsure we want it to be at the most. And so we reject the null hypothesis and we accept, in parentheses, the alternative hypothesis. Keep in mind that we don't accept it indefinitely. We accept it to be true until we can falsify it or we can find a better alternative hypothesis. It needs to be pointed out that there can be some errors in hypothesis testing. This is something that has a couple of terms, so type 1, type 2. I have to admit, I always forget which was which again, because it's not something that we write about all of the time. But when you see someone writing in a paper, well, this might be a type 1 error or this might be a type 2 error, keep in mind that this is something that you can Google and see which was which. But essentially, type 1 means the null hypothesis is rejected, so we think that it's falsified, while in fact, in the objective reality that is out there that we can't necessarily measure, in fact, it is actually true. Type 2 would be the null hypothesis is not rejected, while in reality the alternative hypothesis is actually true. In the two other scenarios where we reject the null hypothesis and we are also right, or we don't reject it and that's the right decision, of course this is not a problem. That's correct. That's simply what we want. Then we have 4 final points on testing hypotheses like this. First of all, it's important to always check the direction. So we looked at the decline in life expectancy. We looked at the increase in life expectancy, and indeed it went up. But it's possible that life expectancy in our data actually decreased, and we didn't pay attention to that. We just looked at the p-value that came out of it. If there would be a significant decrease, we might get the same p-value, and we would conclude, based on not looking at the actual information, that our alternative hypothesis is supported. This is of course not true then, so we need to look at the data itself. By definition, by default, SPSS will show you a two-tailed p-value, which is generally what we want, which means it looks at two directions. So of course SPSS doesn't know whether you're interested in an increase or a decrease in life expectancy, and so it just shows you whether it has changed or not. Yeah, we can get back to this in the lab session if it's not clear. In the scenario that the p-value is larger than alpha, we can say that our test for the alternative hypothesis is not significant, so we can't accept it, we can't reject the null hypothesis, but at the same time, that also does not mean that the null hypothesis is true, because with the alternative hypothesis or the null hypothesis, we can only reject things, we can only falsify, right? So Popper. So we can't really prove the null hypothesis either. And as I said before, but it bears repeating, accepting the alternative hypothesis, the research hypothesis, doesn't make it true indefinitely, but it makes it more likely. We reject the null hypothesis, saying, okay, we can at least show that that's not the case. This makes it more likely that our hypothesis here is true, right? But it's always just more likely. It's never true. In this way, statistics can be very dissatisfying. Finally, I want to spend some words on what's called regression analysis. So we talked about correlation earlier on, and we talked about hypothesis testing. And hypothesis testing we can do through a variety of techniques. One technique might be correlation, but in many cases a better, more versatile technique, which we'll introduce in the lab sessions and in the tutorials, is called regression analysis. And regression analysis has a couple of advantages, but the way it essentially works is that values on y, our dependent variable, are predicted by scores that we have on our independent variable, x. So in the example that we used in the beginning, it would be, for example, is the likelihood that people will vote for the radical right, is that determined by age, by level of education, by income, etc. And so do those values predict one another? Linear regression is what we'll be looking at in this course. I'm pointing this out because linear just means we're drawing a straight line instead of a curved line or some sort of fancy shape, just simply because this is the easiest point of starting. In the future, in follow-up courses, you might learn about other types of regression analysis, and in papers that you find in the library, you might find more exotic types as well. But linear regression is a good sort of way in because it explains the basic principles, and it is still used quite a bit in a lot of fields. And it's a versatile technique that's used a lot. And if you understand the basic principles, this will also allow you to understand the more fancier techniques, at least on the surface level. And so this is also the only equation, the only math essentially that I'm going to expect from you in this course. Y equals a plus b times x. This dot is a multiplication sign, right? Multiplied. So what are we looking at here? So do I have a little graph? Yes, I do. So statistics by definition is about simplifying things. It's never about describing the whole sample. We're not interested in all of these outliers in this scatter plot here. I'm not interested in these people. What we are interested in is the general pattern, so the line that we draw through it. And as you see, it's a straight line. And the straight line is described by this equation. So on the bottom axis, we have x. On the vertical axis, we have y. That's how plots work, right? I'm sure you've talked about this in high school. And so what we're doing is predicting values on y, in other words, how old was the wife, by values on x, in other words, how old was the husband in this example. And to do that, we have a couple of things. We have a, which is the constant or the intercept. Those are different words to describe what this is. And basically a is where the line starts, where this line starts at 0. And then we have b, and b is the slope or the coefficient. In other words, that's how much the line goes up per 1 year of age. So for 1 year of age of the husband, the wife's year of age goes up by b, which is a number. right? Might be one. Maybe if the husband is 1 year older at marriage, the wife tends to be 1 year older as well. But it might be lower than that or higher than that, right? But in this case, it might be close to 1, I'm assuming. This is all that there's to it, to this equation. I don't think it's a very complex one, and of course we'll have time to talk about this and explain it in more detail. But this is the essential explanation, I think. For this lecture, and at the end of statistics lecture, I make sure to have a somewhat silly picture of myself, just to kind of lighten the mood and kind of bring you back to reality after something heavy for many of you. I know that statistics is something that a lot of you are kind of afraid of, and I'll try to make it as simple as I can and make it accessible. And so here we go. This is me in Estonia at some point, not my own baby, but someone else's baby. I kind of forgot whose baby it was at the time. And I thought just my versatility here is just so impressive, because this is I'm also helping a cat over here. I think that's just, there we have it. I'll increase the silliness as we make statistics harder. And for now, I just want to thank you for watching this lecture, and good luck during the tutorials and the computer lab session, where I'll see all of you.